Hello everyone, welcome to the lecture series on VLSI and microelectronics. It is a subject in 7th semester BTech ECE. The course code is EC702. I am Paulo Sridhar, Assistant Professor, Department of ECE, Guru Nanak Institute of Technology. So let us start the lecture series. So today we are in lecture number 17 of the lecture series on VLSI and microelectronics. The paper code is EC702. The total number of lectures in this subject is 45 and it is a 4 credit subject, and the total contact hours is 3 lectures and 1 tutorial. That makes it as a 4 credit subject. Now we are in module 4, that is layout, design rules and fabrication steps of the ICs. Now in module 4 we will be studying the following topics. First is the micron and the lambda design rules, then stick diagram and layout of the CMOS inverter, NAND and NOR gate, fabrication steps of the ICs such as the wafer preparation, oxidation, photolithography, etching, diffusion, ion implantation, metallization and packaging, then CMOS envelope process, and overview of the P-well and the twin tub process. Next comes the course outcomes. The course outcomes are quite important in case of the students because this course outcomes will be fulfilled after the completion of the course. Now, each subject has different set of the course outcomes. Now, in this subject, that is VLSI and microelectronics, we are having 6 course outcomes. Let us see what are the course outcomes. So the first course outcome is able to describe scale of integration, that is SSI, MSI, LSI, VLSI, Moore's law, scaling, short channel effect, VLSI design flow, FPGA architecture, and construct gate level circuit with PAL and PLA concept. Next, second number course outcome is able to analyze CMOS inverter voltage transfer characteristics with the parameters VIL, VOL, VOH, etc. and VTH based on the knowledge of the digital circuits design methodologies like the CMOS, pass transistor, transmission logic, DC-VSL, dynamic logic, NORA logic, able to construct schematic of the combinational sequential circuit, SRAM, DRAM cell using the MOSFET. Third is the based on the fundamental concept of the MOSFET characteristics and model, able to calculate value of the resistance of the current source, MOS diode, current of the current mirror circuit, voltage of references such as the voltage divider, threshold voltage, then the band gap, and the emulate resistance of the switch capacitor circuit, gain of the switch capacitor integrator, and first order switch capacitor filter. The fourth one is with the help of the MOS transistor model, able to calculate the value of the parameters to design the CMOS differential amplifier and two-stage op-amp. The fifth one is able to describe fabrication steps of the ICs and construct stick diagram and layout of the CMOS inverter and basic gates based on the lambda and the micron design rules. The sixth number is able to calculate the gate delay, dynamic power, short circuit power and leakage power, and also the total power consumption across the CMOS inverter circuit based on the derived expression of the delay and the power. Now, among the 6 course outcome, we need to know which course outcome will be fulfilled after the completion of this lecture number 16 of the lecture series on VLSI and microelectronics. Now, this course outcome 5, that is able to describe the fabrication steps of the IC and construct stick diagram and layout of the CMOS inverter and basic gates based on the lambda and the micron design rule. Part of this 5th course outcome will be fulfilled after the completion of this lecture number 16, which normally deals with the fabrication steps of the IC. So let us see what is more in lecture number 16. So this slide is the short lesson plan of this lecture number 16 of the VLSI Microelectronics lecture series, and the course code of the subject is EC702. So we are in module 4, that is layout, design rules and fabrication steps of the ICs, and today we will be studying the diffusion profile, then ion implantation, ion stopping, ion channeling, then implantation, damage and annealing, then etching. Now these are very important topics. So let us start lecture number 16. So before starting lecture number 16, let us have a quick recap of the previous lectures. So in the first lecture, we have studied about the IC technology. That is why we are using the silicon. Next is the IC manufacturing steps. We had seen the pictorial representation of the IC manufacturing technology. Next, we have seen how to design or to grow the crystal. That is the crystal growth, like the silicon crystal growth. And in the silicon crystal growth, we have seen how, considering the many reactions, how the EGS or the electronic grade silicon is being formed. Next, we have seen how to form the single crystal silicon, that is the using the Kurzolski technique, then the float zone technique, then the Bridgman technique. Now this float zone technique is used to grow the single crystal silicon, and this Bridgman technique it is used for designing the germanium and the gallium arsenide single crystal silicon, or growing the germanium and the gallium arsenide single crystal silicon. Okay, next is the wafer preparation. In the case of the wafer preparation, we have seen that the ignot or the single crystal silicon ignot that is being formed, which is cylindrical in shape, is being cut into thin slices, which are called the wafers. And next we have studied about the wafer characterization. In the wafer characterization, we have seen the mobility, Hall effect, and also the lifetime of the carriers. After that, we have started and seen the photolithography and also the photolithographic steps, then the exposure techniques, comparison between different exposure techniques such as the shadow printing, contact printing, proximity printing, projection printing. Then we have seen the basic concept of the clean room. Now, in IC fabrication, it requires a specially designed clean environment, which is generally called the clean room. Next, what is the utility of the mask? Then photoresist, which is mainly of the positive photoresist and the negative photoresist. Then the pattern generation, then oxidation. Mainly the oxidation is of thermal oxidation and the chemical vapor deposition. In thermal oxidation, we know there are two types of oxidation, such as the dry oxidation and the wet oxidation. In the CVD process, we have seen how the graphs are working, and next we have seen what is a thin oxide and thick oxide, and we have started the diffusion in the previous lecture and also studied up to the Fick's law. Now today we will start from the diffusion profile. So let us start lecture number 16, that is the diffusion profile. Now the diffusion profile is a function of the initial and the boundary conditions of the doping. Based on the boundary conditions, the diffusion process is classified into two processes. First one is the constant surface concentration, and second one is the constant total dopant. Now, in the constant surface concentration diffusion process, the dopant supply is maintained so that the dopant concentration at the surface of the substrate is kept constant. Whereas in the constant total dopant diffusion process, the total number of dopant atoms is fixed. Applying the boundary conditions for these cases to the Fick's diffusion law yields two solutions and the two profiles of the dopant distribution. For the constant total dopant diffusion, the profile follows the Gaussian distribution. The diffusion depth is dependent on the time and the temperature used for diffusion. Now, I hope that everything related to diffusion is clear to all of you. Now, let us move to the another process in the fabrication is the ion implantation. Ion implantation is very important topic, and the difference between ion implantation and diffusion is also very important. Please keep this in mind. Ion implantation is another technique for the introduction of the impurities into the surface of the silicon wafer or substrate. Individual dopant atoms are first ionized and they are accelerated. The accelerated ions impulse on the surface and penetrate into the substrate. Now, these are the advantages of the ion implantation. First one is very precise control of the impurities. Number is possible. Next is low processing temperature. Third one is short processing time. Fourth is low penetration depth of the implanted ions. And the fifth is implantation through the thin layers. For example, silicon dioxide Si3N4 is possible. Okay. Now this was in short the ion implantation. Now we will read some topics which are related to the ion implantation, such as the ion stopping, ion channeling, implantation damage and annealing. All this we will be studying in the later slides. So let us move forward. Now we will see what is the ion stopping. When the projected ions move inside the substrate, they undergo several collisions with the electrons and the nucleus of the host atoms. During the collision process, they lose the energy, that is, they lose their energy and finally come to rest. This mechanism is called the ion stopping. Basically, ion stopping, ion channeling, and implantation damage and annealing, all these are the parts of the ion implantation process. So this each and every step is very important, and please rate it very minutely, and also the differences between the ion implantation and the diffusion is very important. I'm repeating this because this is very important for your semester exams. The next topic after the ion stopping is the ion channeling. Now, when the projected ions enter into the substrate, they get aligned with the gap between the host atoms and they travel a large distance before finally coming to rest. This phenomenon is called the ion channeling. Due to ion channeling, the ions become uncontrollable and hence the junction depth goes beyond control. There are several mechanisms to avoid the ion channeling effects. These are given. First one is using an amorphous blocking layer. Second one is disorienting the wafer. And third one is creating a damaged layer at the wafer surface. So these were in short the ion channeling effect. So let us move forward to the next slide. And I hope this slide is clear to all of you. So the next topic is ion implantation damage and annealing. In the ion implantation process, when the highly energetic ions enter into the lattice, they suffer several collisions with the host atoms. Due to the collisions or due to the collision mechanism, the host atoms are dispatched or displaced from their original positions. If the number of the displaced atoms per unit volume becomes comparable to the atomic density of the material, it loses its crystalline property and thus becomes amorphous material. I hope you know what is crystalline and what is amorphous, what is a lattice. Again, all these things you have studied in solid state devices, because solid state device, digital electronics, all these already I told you in the first lecture that these are the prerequisites of VLSI subject. Now this VLSI subject you need, as it is in 4th year, so you need to have the thorough knowledge of the solid state devices and the digital electronics, analog electronics subjects, because in VLSI we are making the devices with the CMOS technology, and CMOS, as you know, it is very efficient because of its so many advantages, like it consumes less power, like this. Okay, now let us come back to this lecture. Now to rectify the damage caused by ion implantation, a methodology is used which is known as annealing. Annealing heals most of the damage. In this process, the wafer is treated alternately in very high and low temperatures for a long time. Now, as I was telling that this lattice, crystalline, amorphous, all these we have studied in the solid state devices. Now, as in VLSI technology, we are using the CMOS fabrication, and we are here to read the CMOS fabrication or the fabrications of the ICs. And we are mainly using the CMOS technology. CMOS, it requires less space, it is more and more efficient. That's why we are using the CMOS technology. Now I hope this slide is clear to all of you. Now let us move to the next slide. That is the etching. Now etching is also a very important process in the case of the fabrication of the devices. Now etching is the process of selective removal of some portions of a layer. The photolithography technique is used to create patterns of the silicon wafer. It involves the etching process which removes the selected portions of the layer. Etching is of two types, isotropic and anisotropic. What happens in an isotropic etching? Each rate is small or is same in all directions, and in anisotropic etching, etching rate is not same in all the directions. Now, the degree of anisotropy is defined as A is equal to 1 minus of L by V, where L is the lateral etch distance and V is the vertical etch distance. Now let us move to the next slide. Now this figures illustrates the anisotropic and the isotropic etching process. You can see that here this is a slow etching where the crystal plane is 111 and this is the etch mask. Okay. Now this one is a V-cut etching and this one is a round etching and this one is the L and this one is the L, means this is the longitudinal edge and this is the vertical edge, as you can see in the formula of the degree of anisotropy, that is A is equal to 1 minus of L by V. I hope this is clear to all of you. That is anisotropic and isotropic etching. Next is the wet chemical etching. Now you see here that an agent is a chemical solution that reacts with the layer that needs to be etched out. Depending on the material to be etched out, the chemical solution differs. The etchant solution is either sprayed on the wafer or the wafer is dipped into the etchant solution. This type of etching is known as wet chemical etching. Wet chemical etching is isotropic in nature. In this process, the etch rate is same in all directions. An example of the anisotropic etching is the etching of the crystal plane 111, which results in a V-shaped side walls when etched in a hole or in 100 silicon wafer in the potassium hydroxide KOH solution. This is the figure. This is the H marks, and this is the example of an anisotropic etching. This is the V cut. You can see V-shaped sidewalls are there. This is the V-shaped sidewalls, and there is a slow etching of 111 crystal plane. This gives rise to 111 crystal plane. Okay. Now let us see the next slide, that is the dry etching. Now you can see here the dry etching is of three types: reactive etching, then spurter etching, and vapor phase etching. Now dry etching is used when vertical sidewalls are required, or when thin films with small feature resolutions are to be obtained. Dry etching is also known as plasma etching. Plasma is a mixture of ionized and unionized gas molecules. It is produced by applying a very high electric field to a gas. And dry etching is also very expensive compared to the wet etching. Now let us move to the next slide, that is the reactive ion etching. The reactive ion etching is also known as RIE. That is, in short form, it is RIE. The substrate is placed inside the reactor in which several gases are injected. Plasma is created in the gas mixture using an RF power source, breaking the glass molecules into ions. The plasma ions move towards the surface and react with the material being etched to form another gaseous material. This is known as the chemical process of reactive ion etching. There is another part which is called the physical part, which is similar in nature to the sputtering deposition process. If the ions have high energy, they can knock out atoms of the material to be etched without a chemical reaction. The chemical process is an isotropic, and the physical process is anisotropic in nature. Combining the physical and the chemical processes, it is possible to control the anisotropy of the etching to form sidewalls that are shaped from the rounded to vertical. Now this is the schematic of the reactive ion system. Here you can see there is a plasma. These are the wafers. These small things are the wafers, and this is the RF signal insulator. This is the upper electrode. This is the lower electrode, and also there is a wafer holder. This is the diffused molecules or the diffused nozzles through which there is a diffusion. Gas is going inside, and through pump it is coming. And again, this is the plasma etching. So I hope this plasma etching or the reactive ion etching is clear to all of you. So we have come to the last part of the lecture. So thank you all for being with us and attending this class and hearing this lecture. Hope to meet you soon. Thank you all again.